Okay, let's start. So for our next speaker is Antonio Sollima from Bologna University. And please, Antonio, you have 35 minutes plus 5 minutes for discussions and questions. Please.
Okay, so thank you. First of all, I want to thank the IASBS and Hossein to invite me here at your national meeting. So today I will review some recent advances in the characterization of the initial mass function in galactic star clusters and in the solar neighborhood, also in the light of the new and upcoming photometric, spectroscopic, and astrometric surveys, which are providing us a wealth of data which are changing our picture and our perspective in the determination of this important parameter. So first I start with the definition. So we can define the initial mass function as the function describing the proportion of stars as a function of their masses. So for instance, if you consider stellar population or a gas cloud in which the star formation is onset, so you will have that a part of this gas is used to form high mass stars and other will be used for low mass stars. So the relative proportion of these high mass and low mass stars defines the mass function, which is usually defined as the number of stars per unit mass, even if there are some alternative definition in which a logarithmic mean in mass is used, but one can of course translate one to the other definition easily. So generally, the analytical description.
Antonio,
Yes?
sorry.
What happened?
We cannot see your screen.
Screen. So you see my first slide, or you don't see anything?
It seems it's stopped.
Sorry. I don't know why.
You should share your screen again, please.
I try to share it again, but okay.
Yes, we can see it.
Okay. So I hope you arrived at this stage. So have you seen this slide? Okay. Have you seen this slide? Can you hear me? Can you hear me?
Yes.
Oh. Yes. Okay. So start again from here. So okay. So the typical analytical description of the IMF is generally a decrease in power law or a log normal distribution, and this is because usually it is easier to form low mass stars rather than high mass ones. So the importance of the mass function is crucial in many aspects of astrophysics, just because this ingredient is something that you need if any time you want to simulate any kind of integrated stellar population. So for instance, here in this plot I show the colors versus mass to light ratio of an integrated stellar population, a simple stellar population, if you change the mass function. And since different stars of different masses contribute in different way to colors, mass, and light, so you have that if you change the relative proportion of them, you can change also the track in this diagram. And the color can change by 1 magnitude, and the mass to light ratio by a factor of 3. Also, the dynamical evolution of stellar population change, or stellar system, for instance, because if you change the mass function, you change the mean mass, and so actually you change all the time scale in which the low mass stars make friction to the high mass ones. And this is shown here, where you can see the different evolution in mass and Lagrangian radii of two stellar population, two star clusters with different IMF. But also you change also the chemical evolution of a stellar system, because stars, in particular massive stars, produce different amounts of chemical elements as a function of their masses. So if you change the relative proportion of these stars, you change also the amount of these elements which is which pollutes the interstellar medium. So if you change the mass function, for instance, in this plot, you can see that the nitrogen over oxygen abundance change by 0.7 dex. So usually when I start a talk, I usually give an introduction also on the theoretical framework. In this case, it is quite complex because since more than 50 years, there are two competing theories which fight together, and both of them are very accurate, but it is difficult to understand who is right. So I'm not an expert of star formation, so I will just give a brief outline of both of them. So in the first, assumes that the distribution of masses is determined by the fragmentation of a molecular cloud. And this fragmentation occurs on scales which are of the size of the Jeans mass. So in practice, if you have an homogeneous distribution of gas, then you will have small dishomogeneities forming, and when one of them becomes more massive than the Jeans mass, you have a local collapse. Of course, this collapse can occur in a single event, forming a massive star, or in a in a series of events in which you progressively form many low mass stars when locally this Jeans mass criterion is satisfied. So this is the reason why it is easier to form many low mass stars than a single high mass star. If you look at the definition of the Jeans mass, the usual definition depends on temperature and on density and the molecular weights. Of course, these quantities are interconnected according to the different processes which can occur, and these lead to different power law as a function of density and molecular weight. But in any case, what matters here is that the Jeans mass depends on the chemical composition, because chemical composition affects the molecular weight. So you expect that the IMF depends on chemical composition. Of course, this is not the entire picture, because if otherwise you would expect also that the fragmentation would produce more low mass stars when there is more dense region, because the Jeans mass depends on a negative power of the density. And this is not in agreement, disagrees with the evidence of primordial mass aggregation in young clusters. But this is solved because in the global picture, so this is only the first stage, the fragmentation, where you form only the core of the stars. But in this first stage, so the gas still dominates and is accreted with more efficiency in the center. When the gas is exhausted, so stars virialize, and then the massive stars accrete on the Bondi Hoyle rate. Now, the Bondi Hoyle rate is has a steeper dependence on the mass. So what happens is that more massive core accrete more gas, and so this produces a steepening of the mass function. If you see, both the tidal limit and the Bondi Hoyle limit are dependent on the radius, as a decreasing power of the radius, and a positive power of the mass. So the fact that massive cores accrete faster than less massive cores is the so-called competitive accretion, produce the steepening of the mass function in the center, and the dependence of the accretion rate on the radius produce the primordial mass aggregation, which is the same which is observed. The other theory make a kind of consideration and says that, okay, this is a typical star-forming region, S106. And you can see that here, the density and temperature conditions are completely inhomogeneous. And there are many regions in which the Jeans mass is very different. So this says that it is impossible to define a single Jeans mass in this situation. And the mass function cannot be determined by these parameters. But they say that the stars self-regulate their masses by balancing the inflow of gas with the outflow produced by the ramp ratio. And so the mass depends on many parameters, in particular the speed of sound is the main parameters, but also many other efficiencies, like, I don't know, the efficiency of accretion of the disk, or the fraction of gas which is actually used to form the star, and also by the rotational properties. So there are many parameters involved in this process, and all of them do not have a single value, but they follow different distribution. And when you convolve all the distributions, for the central limit theorem, you obtain a log normal initial mass function. Since the speed of sound depends on density and the molecular weight, also in this case, the IMF is expected to depend on density and metallicity. Now, it is very difficult to distinguish between these two theories because both of them predict a similar shape of the IMF, which is expected to be log normal with a peak at low masses and then a declining profile. But they also predict a very similar dependence on metallicity because as the metallicity decrease, you have a shift toward the high masses of the peak because it increased the Jeans mass in one theory and it increased the thermal velocity, which set the lower limit for the speed of sound in the other theory. But also it increased also the limiting mass at the high end because it increased the Eddington luminosity. So in practice it is possible to form more massive stars which are stable. Anyway, even if it is impossible to distinguish between these two theories, just looking at the mass function, anyway, it is important to test if the mass function observed in real stellar system looks like the one predicted by these theories and follow the same dependence on the metallicity. Because till now, there are still not enough evidences for universal or varying initial mass function. So it is, and the shape of the mass function is still not clearly defined. Okay, so when you look at the mass function and you look for the IMF, so the initial mass function, you have to take into account the fact that the mass function is affected by the dynamical evolution of the system and also by stellar evolution. So if you want to understand how the IMF is made, you need to observe it in dynamically unevolved stellar system, so system with an alpha relaxation time which is much longer than the age, or very young systems. So these are typical dynamically unevolved stellar system, and now I will review the new advances in the IMF in this environment. So the first environment is the solar neighborhood, which is made by all those stars which are in the neighborhood of the sun. So this is the natural sample in which the IMF is studied, and just because these stars are very, very nearby, so it's easier to make a complete sample of them, census of them. The problem is that if you look at the observational color magnitude diagram, which is shown here, of the stars within 150 parsec, so this is very confusing and doesn't tell you anything about the mass function because the location of the stars in magnitude is not univocally connected to their masses, but also to their distances, because stars between 1 and 25 parsec span more than 7 magnitudes in distant modulus. So to convert these apparent magnitudes in absolute ones, you need the knowledge of their distances. And this is now possible thanks to the parallaxes provided by the Gaia mission, who in its release now provided very accurate parallaxes with a precision down to 20 microarc seconds. And so thanks to this survey, it's now possible to convert this apparent colorimetric diagram in an absolute colorimetric diagram, where now the location of the stars along the main sequence are univocally connected to their masses, and this is possible to reach even very faint magnitudes with a good level of completeness.
Moritz Hazelbauer.
Now, on the top part of the main sequence, instead, there is a paucity of stars. And this is a feature which is spuriously produced by stellar evolution. This is shown here, where you can see that a typical power law stray from the observed number counts at masses above the 1 solar mass. And this is due to the stellar evolution because a fraction of these stars already evolved, so are no more visible. And this can be understood if you consider a single burst of star formation, which can follow a power law mass function. But if you add a second burst after 50 megayear, the global mass function will present a step, which is produced by the fact that part of the stars are still there, the newly formed stars, but the older stars already evolved in the high mass hand. And if you pass from 2 to 5 bursts, so this is even more evident, where you start to see that this is no more a step, but is a transition with a steepening of the mass function. And in the limit in which you use a continuous star formation, continuing over an Hubble time, what happens is this one, which is very similar to what you observe. So all of this is just to say that if you want to determine the mass function, you have to consider two different regimes. One at masses below the currently evolving mass, in which the present-day mass function is reminiscent of the IMF. And then other at the larger masses, so more than 0.8 solar masses about, which is the currently evolving mass, in which if you want to derive the IMF, you have to take into account for the star formation history. Other complications are also linked by the presence of binaries or the presence of stellar population gradients in the stellar in the solar neighborhood. So the techniques which are used are mainly two. So one is the older one, which directly connect the luminosity function to the IMF, just using the mass luminosity relation or given isochron and the star formation rate, so the star formation history, which is assumed. This is the technique adopted by Salpeter in 1955 in the first studies, allowed to derive, so to convert the luminosity function into mass function. This is the advantage of this technique, is that it is very simple, but the drawback is that it is quite difficult to include second-order complication, like, for instance, the effect of binaries or the effect of stellar population gradients. So now the modern techniques are instead based on a full forward simulation of the color magnitude diagram of the solar neighborhood, in which you produce a synthetic stellar population, in which you include all the desired ingredients, so binaries, stellar population gradients. Then you simulate also the effect of incompleteness and photometric errors, and then you can compare directly the luminosity function of the mock observation with the observed one, and you can tune the mass function to reproduce in the bottom part of the diagram just the luminosity function, and in the top part of the diagram for the more massive stars also simultaneously the color magnitude diagram by tuning both the mass function and the star formation history. So in this is, for instance, what I did in recent papers in 2019, where I derived the mass function of the solar neighborhood using Gaia data. And these are the results for different assumptions of the binary fraction. So you can see that the binary fraction affect the determination of the IMF, in particular in the bottom part. This is because the largest is the binary fraction, the higher is the fraction of blended sources, because you see just the contribution of both the component of the binaries, and also higher is the fraction of stars, low mass stars, which are hidden as secondary components. But anyway, for any reasonable assumption, the binary fraction, here you can see that the mass function show a peak at low mass stars, more or less about 0.15 solar masses. And this is the first time that this peak is noticed in the mass function of the solar neighborhood, and this agrees with the prediction of star formation theories, and is connected to the log normal shape of the IMF. So now if we compare the determination of the mass function in the solar neighborhood in studies performed before the Hipparcos and Gaia missions, you can see that this study all agrees with a mass function which shows a power law slope with an index of about -2.3 for massive stars, and then a flattening at low mass stars. This is confirmed by later studies, where, however, after Hipparcos and Gaia, the higher part, the mass function appears to be steeper, so at masses above 1 or 2 solar masses. And this is confirmed also after Gaia, where, however, here, as I showed you before, it is apparent now also the turnover at low masses. Now, besides the solar neighborhood, we can have other environments where the IMF can be studied. One of them is the young massive clusters, which are those clusters younger than 100 megayears and more massive than 10 to the 4th solar masses. So these are quite valuable because they are formed by single stellar population. So all the stars have the same metallicity, are located at the same distance, and so it is easier to convert their luminosity function into mass function. The problem is that all these systems are quite far away, so the uncertainty at which we can determine their mass function slope is quite high. And indeed, if you look at the recent studies on the slope of the mass function in this stellar system, the dispersion in the measured slopes is large, but still compatible with universal IMF within the uncertainties. So it is not possible to exclude variation included in 0.5 dex. So actually this test is more or less inconclusive. A better results comes from the dwarf spheroidal galaxies, which are more extended over a much larger extent. So the relaxation time is longer than the Hubble time. So we are sure that here collision effects are not at work. And also because they are all very metal poor, we can assume them as a single stellar population, even if it is not true, but in this case, the models change very few in that range of metallicity. So we can make this approximation. And because of their distances, it is possible to reach, with space-based photometric studies, the mass function down to 0.5, 0.4 solar masses. The interesting thing is that if we analyze the slope of the mass function in these 6 nearby dwarf spheroidal galaxies, we can see that they correlate with the velocity dispersion and with the metallicity. And in particular, with the metallicity, we can see that the more metal-rich galaxies have a steeper mass function, which is in agreement with what is expected from star formation theories. And so, would suggest an indication that of the IMF variations. However, you have to consider that the limiting magnitude of these studies is quite shallow, and close to the limiting magnitude, you can have also fluctuation due to the Poisson noise. And since there is a relation between the mass of these galaxies, so the strength of this Poisson noise and the metallicity, so these can produce a spurious trend of the mass function with the metallicity. So one have to take this result with much care. Another possibility is to use early type galaxies, which are even more massive and more extended. So in this case, the relaxation time is much, much longer than the Hubble time. Here, the problem of their distance is dramatic because we are so distant that it is impossible to resolve individual stars. So their mass function can be only guessed using integrated spectroscopic indexes, because if you consider the integrated spectrum of stellar population, there are indexes which are more sensitive to metallicity and others which are more sensitive to gravity. So gravity means, since stars of different masses have different gravities, you can use this indicator as an indicator of the mass function. So you make a lot of assumptions so that on the metallicity distribution and on the power law shape of the mass function, but in this case you can compare these two indexes and you see that there is a correlation. And also in this case, the more metal-rich early type galaxies are also those which should have a steeper mass function. So in agreement with what's found in dwarf spheroidal galaxies and what's predicted by star formation theories. Also in this case, however, one has to take care because these indexes have many assumptions below, and also there could be some covariances between these indexes, which are not well reproduced by models. So there is possible degeneracy also with star formation history, age effect, and so on. When one move from dynamical unevolved to dynamical evolved stellar systems like globular cluster and open cluster, so now one cannot neglect anymore the dynamical effect, but anyway, there are many important results which can be obtained. So let's start with the globular clusters. So globular clusters are very useful for the determination of the mass function because there are plenty of globular clusters in the nearby universe with more than 80 globular clusters within 10 kiloparsec. And also the mass function. Globular clusters can be derived with very good accuracy and completeness down to the hydrogen bonding limit thanks to HST photometric studies. The problem here is that the relaxation time of these stellar systems is smaller than their age, and so what happens is that the ever continuing interaction between stars produce an exchange of kinetic energy between them. And since the amount of kinetic energy exchange is proportional to the ratio of the masses, so this produces that the effect that high mass stars transfer kinetic energy to low mass ones. So you have a correlation between the orbital energy of the stars and their mass. This is a twofold effect. So the first is that the low mass stars have higher orbital energy, and so they are more prone to evaporation. So if you look at the evolution of the mass function in time, you can see that the mass function starts to be depleted in low mass stars as the evolution proceeds. And so if you observe the mass function after many gigayears, so at the present day, this is much more flatter than the IMF. And so it is not more representative of the initial mass function. The other effect is that since the high mass stars have low orbital energy, they sink into the cluster center. So if you observe the mass function in the center of the cluster, you observe a top high mass function, which is not representative of the global mass function. So this means that you have to correct this effect if you want to determine the IMF. Now, analyzing the literature studies on the globular cluster mass functions, there are many confusing and controversial results. Indeed, there are made in the early 90s, which show that the mass function of the globular cluster depends on the position of the cluster in the galaxies. Other which suggest that it depends on the strength of the tidal field. Others which depends on the concentration of the cluster, and other which indicate a dependence on the density. So all these apparently conflicting results depends on the fact that all the studies made in the 90s and the early 2000s years were based on shallow surveys made on analysis made with a very restricted field in the center of the cluster. So where the correction for mass segregation and for completeness were very high. So they produced very uncertain results. But this changed dramatically after the advent of the Global Cluster Trajectory Project, made with the Advanced Camera for Survey on board HST, which allowed to determine the mass function of more than 35 globular clusters at very faint magnitude limits. And based on this study, we will be able to determine the mass function of all these globular clusters, which appears to be flatter than the typical salpeter mass function. So if we fit with a single power law, we obtain slopes between -1.8 and plus 0.1. So this is, of course, due to the dynamical effects that I told you before. But if you select only those clusters with a very steep mass function, so these are those which should be closer to their initial mass function, because are the less evolved clusters. And if you consider, for instance, the power law fit of all these mass functions, and you separate cluster in a cluster with a slope steeper than -1 and less steep than -1, so you can see that the residual of this fit correlate with mass. And this indicates that if you take the stars, the cluster, the less evolved clusters, the shape of the mass function is band, is not just a single power law, but as a kind of band which implies a lower now, a depletion of low mass stars, in agreement with what you expect if you start with a Krupa or Chabrier mass function. While instead, if you take the more evolved cluster, the power law is more or less is a good approximation. And this agrees with the prediction of n-body models, which show you that in the first stage of evolution, the mass function is reminiscent of the initial mass function, as only a slow evolution, while in evolved cluster, all the features of variation of the single power law are erased by stellar evolution. So this is the reason why you don't observe any significant residual in evolved cluster, and you do observe it in less evolved ones. Okay, so another interesting feature regards the correlation with the various parameters. And this is shown many correlations between the mass function slope and various parameters. Many of them are scatter plot. So the only significant correlation is the one with the half mass relaxation time. With the cluster which have a longer relaxation time, which have a steeper mass function. And this is in agreement with what you expect, because if two-body relaxation is the main process leading to the evaporation, the evolution of the cluster, so you expect that the less evolved the cluster is, the longer its relaxation time, the less should be the strength of the dynamical evolution, so the evolution of the mass function, which should be steeper. This is even more clear if you plot it as a function of the number of elapsed relaxation time, so h over the relaxation time. And here you can see that the shape of this distribution is very tight, with a very small scatter, less than 0.2 depths. A small scatter implies a little room for IMF variation. Because if there would be IMF variation, you would expect that this scatter would be propagated through the evolution. So this means that the whole global cluster were born with the same IMF. But even more interesting is that if you compare this with the typical track of evolution, adopting a Krupa mass function, this is completely off from the locus of the observational points. While instead, if you change the break mass to higher masses, the agreement turned out to be better. And this is in agreement with what you expect from the dependence of the mass function on the metallicity. Because to move the break mass at higher mass means that the mass function is flatter in the bottom part. And a flatter mass function is expected in globular cluster because our low metallicity stellar system, of population 2 stellar system. So this agrees with expectation that in low metallicity environments, the mass function is flat. Of course, a good test to this would be to observe the galactic counterparts in the high metallicity of globular cluster, which are the open clusters. And there are many open clusters in the local universe. Of course, here the problem is that you have a strong contamination from the field. But now, in the new era of the Gaia surveys, this is also overcome to this problem, because now you can select members of open clusters, not just using the photometric parameters, so color and magnitude, but also using parallel axis and proper motions. This is a work which has been done by Hamid Ebrahimi and will be part of his talk, so I will not spoil his results. But I just want to show you that if you put all together the mass function slopes of Milky Way, LMC, SMC, globular cluster, both spheroidals, and the open cluster with selecting only those systems with a number of elapsed relaxation time smaller than 2, so the unevolved or poorly evolved stellar system, the trend with metallicity is now clearly apparent. And also in this case, this agrees with the prediction of the star formation theory, so with the most metal-rich system, which with a steeper mass functions. So summarizing the results, after many years of work now, the shape of the IMF, at least in the solar neighborhood, appears to look like more similar to what is expected from star formation theories, with a peak at about 0.15 solar masses, which should be connected with the log normal shape of the IMF, with an increasing stiffness at high masses. And this is also confirmed by the shape of the mass function in the poorly evolved globular clusters. And this so is in agreement with what we expect from the theories, and now is coming to light, so after many years of works. And also, if we consider the slopes of the mass function in different stellar systems, so encompassing many orders of magnitude of mass, radii, and chemical composition, we can see that low spheroidal, early-type galaxies, unevolved globular lobar clusters, all shows that the mass function slope, at least in the low mass end, is a dependence of on metallicity. So the IMF now appears to be non-universal, with a good level of significance now, which is also disagrees with the prediction of star formation theories. A new perspective are expected in the near future because of the advent of many spectroscopic wide field surveys, which are expected to sample the chemical properties of individual stars in the solar neighborhood. So Lamos, Weave, and also Gaia will allow to derive the metallicity of individual stars. So it will be possible to calculate the mass function in beams of metallicity for individual stars. And this will allow to confirm the dependence of the IMF slope as a function of metallicity, but also as a function of many other chemical patterns. And also, when the 40-meter class telescopes, so ELT, TMT, GMT, will be available, all of them are equipped with photometric cameras. And the large diameter of this telescope will allow to have exquisite resolution using adaptive optics techniques. And so it will be possible to resolve young massive clusters also outside the Milky Way, and also a few nearby early-type galaxies. So it will be possible to determine the mass function, as we do now for galactic stellar system, also outside the Milky Way. So to study also the effect of the environments on the IMF. But that's all. Thank you very much.
Thank you very much, Antonio. So we have time for 1-2 short questions. Any questions? Yes.
Hi, thank you for the talk. So you mentioned that mass function depends on different parameters, and you described the phenomenological data. But I want to ask that, do we have an analytic model that takes into account all of these parameters like metallicity and velocity dispersion?
Okay, so I don't have, but there are all these works from both the group, so one of Adam Cepatuzzo, or the other is the one from the group of Bate and Bonnell or Chabrier, or the Chabrier group name. The problem is that they are very complex models, and also actually the dependence on metallicity and density are very, I would say, they produce very, very small variation in the mass function, and also they are quite difficult to be tested. But more of them are, many of them are just produce a shift in the peak of the log normal distribution, rather than a change in the slope, in the shape or in the slope, because all of them include the convolution of many distributions. So actually, the shape of the mass function is always to be log normal or log normal like. So what changes? Just the peak of the distribution.
Okay, thank you, Antonio. Other question? If there is no more question, please thank Antonio again.